For thousands of years, the great civilizations of the world, Egyptians, Babylonians, Greeks, built wonders that still defy modern explanation. They aligned monuments with celestial bodies, calculated planetary cycles with astonishing precision, and designed structures so mathematically perfect that they have withstood the test of time for millennia. And yet, through all of this, there was something they did not do. They did not use zero. Think about that. The mathematical minds that gave us the pyramids, the Parthenon, and the Antikythera mechanism, the engineers who laid the foundations of civilization itself, had every opportunity to invent and use zero. And yet, for thousands of years, they deliberately ignored it. Was this an oversight? A simple case of no one thought of it, or did they think of it and reject it? What if, far from being a forgotten breakthrough, zero was an idea that was known and dismissed again and again by those who understood its implications better than we do today? What if the real question isn't why it took so long to discover zero, but rather why it was finally accepted, and what was lost when it was? Zero is often presented as one of the greatest intellectual achievements of human history, a symbol of progress, of mathematical sophistication, of the power of abstraction. And indeed, it is. With zero came the decimal system, algebra, calculus, and, eventually, modern computing. But zero also did something else, something that the ancients may have feared all along. It detached mathematics from reality. Before zero, mathematics was deeply relational. It was about proportions, about tangible interactions with the physical world. A builder didn't need to know an equation. He needed to know that a structure twice as tall required a base twice as wide. A merchant didn't need to solve for X. He needed to know the ratio of goods exchanged. Numbers weren't abstract. They were tools for describing relationships. But zero changed that. It introduced a way of thinking that had never existed before, a way that prioritized symbolic manipulation over direct physical intuition. This may explain why, for most of history, practical mathematics resisted zero. The medieval masons who built Europe's great cathedrals had no use for it. They worked as their ancestors did, through proportions, through ratios, through geometric intuition. Even as mathematicians in distant universities wrote equations with zero, the men who actually built the world saw no advantage in it. If anything, the introduction of zero coincided not with an era of mathematical flourishing, but with its decline. It was not the dawn of the Enlightenment, it was the Dark Ages. This is where the story of zero takes on a different character. It was not simply discovered, it was adopted in a time when much of the accumulated mathematical wisdom of the ancient world had been lost. And that forces us to ask, was zero truly an advancement, or was it simply a necessity for a world that had forgotten the old ways? Whatever the answer, one thing is clear. Zero did not simply expand mathematical understanding, it divided it. It marked the point where mathematics began to split, where the once universal language of ratios and proportions gave way to a world of symbols and abstractions, accessible only to an intellectual elite. For over a millennium, that elite would push mathematics further and further into abstraction, severing it from its practical origins. The result? A world in which mathematics became something to be feared rather than mastered, an opaque and rigid system of rules rather than a natural, intuitive language. We see the consequences of this today. Most people view mathematics as alien, something that only experts can understand. Yet the ancient world teaches us this wasn't always the case. Mathematics was once intuitive, relational, and universally accessible. And so today, we must ask, what was lost? And more importantly, what can be reclaimed? Zero may have been inevitable, but it was not the only way forward. What if we could restore the relational, proportional methods that guided the greatest builders of history? What if we could blend that intuitive mathematical wisdom with the power of modern computation? By doing so, we could make mathematics more accessible, more creative, and more innovative than it is today. To understand how, we'll trace zero's journey through history, exploring its influences and impact. But first, we must explore where we came from. We must journey back to the time before zero, to a world where mathematics was built not on abstract symbols, but on the fundamental relationships that govern the universe. Before the rise of zero, before mathematics became the abstract and symbolic system we know today, there was another way, an older way. A way in which numbers were not mere placeholders in equations, but reflections of the natural order. In this world, mathematics was not a detached exercise of the mind. It was a living language, inseparable from the land, the stars, and the hands that shaped civilization itself. It was a mathematics of proportions and relationships, of harmony and structure, of builders and astronomers who did not calculate for calculation's sake, but to bring order to the physical world. And yet, as advanced as this mathematics was, it did not use zero. It did not need zero. For thousands of years, the greatest civilizations built wonders that still stand today, wonders that embody an understanding of mathematics so precise that modern engineers still marvel at them. The pyramids of Egypt, the astronomical calculations of the Babylonians, the elegant geometric proofs of the Greeks, all achieved without the concept of zero. Was this because they simply never thought of it? Or was it because, knowing what they knew, they saw no advantage in it? To answer that, we must journey back into this world and understand how numbers functioned before the void was given form. Let us begin with the Egyptians. These were not a people of abstractions. They were builders, surveyors, traders, people whose mathematics had to be as practical as the land they lived on. They understood relationships, and from those relationships, they could determine everything they needed to know. They measured their world in fractions, not floating-point decimals, because their reality was one of dividing food, measuring land, and balancing trade. And yet, they were capable of extraordinary feats. Look at the Great Pyramid of Giza. Even today, its dimensions align with the golden ratio so precisely that some claim divine intervention must have been involved. But there was no need for divinity, only an intuitive grasp of proportion. The Egyptians understood that by maintaining the right ratios, they could scale a structure to any size without error. They didn't need a zero to hold their place in an equation. They needed only the relationships between lengths and angles, weights and balances, time and motion. And they were not alone in this approach. The Babylonians, masters of astronomy, devised a number system based on 60, a system so effective that we still use it today to measure time and angles. They predicted eclipses, mapped the movements of planets, and kept records of trade that stretched across empires. Systems were flexible, using bases that better accommodated their necessary ratios than the rigid limits of decimal arithmetic. And they did it with tables of proportions, sequences of ratios that preserved the relationships between celestial bodies without requiring a symbol for nothingness. And then there were the Greeks, the philosophers of number and form. They were not content merely to use mathematics. They sought to understand its very nature. To them, numbers were not abstract symbols, but manifestations of reality itself. Mathematics was geometry, a sacred discipline in which every number was a shape, a space, a physical truth. To the Greeks, a number had to exist, in the same way that a line or a circle existed. But zero was not a thing, it was an absence. And absence, they reasoned, was not a number at all. So they built their mathematics on constructible numbers, on forms that could be drawn, measured, and understood. They knew of irrational numbers but distrusted them. They knew of voids but did not count them. They studied the harmony of the spheres, the mathematics of music, the proportions of architecture, always seeking what was real, what was intuitive. For them, numbers did not float in an empty, abstract void. They lived in stone, in the arc of a temple column, in the rhythm of a lyre, in the paths of the stars. And so, for millennia, this was mathematics. Not an abstraction, but a tangible experience of the world. If this mathematics was so effective, so powerful, so deeply in tune with nature, why did it not endure? The answer is not that it was inferior, nor that zero was a revolutionary discovery that suddenly made all prior mathematics obsolete. Rather, the world itself changed. And when the world changed, so did the way it measured itself. The limitations of pre-zero mathematics were real. Large numbers were cumbersome. Without zero, there was no clean way to represent negative numbers or to structure algebraic equations. There was no single, universal framework to unify arithmetic, algebra, and geometry. And so, when the old civilizations fell, when the libraries of Alexandria burned, when the Greek academies faded, when the ancient knowledge of proportions and relationships was scattered, mathematics did not evolve, it had to be rebuilt. But what was rebuilt was not what was lost. Instead of rediscovering the proportional, intuitive mathematics of the past, the New World took a different path. A path of symbols, abstraction, and formalized rules. A path where zero, once ignored, became essential. A path where numbers were no longer tied to the physical world, but instead existed in an infinite space of their own. This was the birth of the mathematics we know today, and with it came both great power and great loss. For thousands of years, mathematics had been the bridge between human understanding and the natural world. But with the rise of zero, that bridge began to crumble. It was a shift that would redefine how we think, how we measure, and how we build. A shift that would divide mathematics into two worlds, the world of the practical and the world of the abstract. And so, as we step forward into the age of zero, we must ask, was this shift truly an advancement? Or was it a necessity born of forgetting what came before? Let us now explore what happened when zero entered history, and how mathematics was changed forever. For thousands of years, mathematics had been grounded in the tangible. It was a system of proportions, relationships, and constructs that mapped onto the real world. It was a tool used by artisans and architects, navigators and astronomers, a language spoken by those who shaped civilizations. And then something changed. A new number emerged, a number unlike any other. A number that did not represent a thing, but the absence of a thing. A number that stood not for quantity, but for nothingness itself. Zero. With its arrival, mathematics took a sharp turn away from its relational roots and towards something far more abstract. And with that turn, a new kind of mathematics was born. One that would come to dominate the modern world, but in doing so, would also divide it. How then did zero appear? And why did it take hold not in the age of the pyramids or the golden age of Greece, but only after the decline of those civilizations? To answer that, we must look to the land where zero first gained a foothold, a land of deep philosophical inquiry where mathematics was not just a tool, but a reflection of something greater. It was in India, sometime around the 7th century CE, that zero first emerged in its complete form, not just as an empty space in a numerical system, but as a number in its own right. Indian mathematicians had long worked with place value systems, and they recognized a crucial truth. If a numeral system was to function efficiently, it needed a way to distinguish between absence and presence. Other cultures had placeholders before them. The Babylonians used a space, the Mayans used a shell. But the Indian mathematicians took the concept further. It was Brahmagupta who first formalized zero, giving it rules and operations. He defined how zero should behave in equations, how it interacted with positive and negative numbers, how it could be added, subtracted, and multiplied. But what is more fascinating is how this concept emerged not just from practical necessity, but from philosophy. Indian metaphysical traditions had long explored the idea of shunyata, the void, a fundamental concept in Buddhism and Jainism. To them, nothingness was not merely an absence. It was a presence of its own, a state that had meaning. And so, mathematics followed philosophy. The void was given a name, a shape, and a role. And with that, zero entered the world, not merely as a convenience, but as a radical redefinition of what numbers could be. Yet even in India, zero did not immediately replace ratio-based thinking. It was seen as useful, but not revolutionary. It was only when zero began to spread beyond India that it took on a new and more transformative role. From India, zero traveled westward, carried by the scholars of the Islamic Golden Age. The Arab world at that time was a center of learning, preserving Greek texts, expanding upon Indian discoveries, and developing new mathematical systems that would shape the world to come. It was here that zero became embedded in algebra, a discipline named after the work of Al-Khwarizmi, who systematized equations using this new notation. With zero, algebra could now express not just known quantities, but unknowns, absences, and negatives. And it was here that mathematics began to split. For while practical mathematics, the mathematics of builders, merchants, and artisans, remained firmly rooted in proportions and geometry, a new kind of mathematics was being developed in the universities of the Islamic world. A mathematics that was no longer about tangible relationships but about symbols and rules, about manipulating numbers as abstract entities, rather than as representations of real-world measures. This was the birth of symbolic mathematics, and with it came a transformation. Mathematics was no longer something to be visualized, but something to be calculated. But even then, zero had not yet conquered the world. It still had to pass through one final gate, the medieval world of Europe, a world that had already lost much of its mathematical heritage. By the time zero reached Europe, much of the mathematical wisdom of antiquity had been lost. The geometric insights of the Greeks, the proportional reasoning of the Egyptians and Babylonians, all of it had faded, replaced by centuries of stagnation. And it was in this intellectual vacuum that zero found fertile ground. The introduction of zero into Europe came primarily through Leonardo Fibonacci, the Italian mathematician who, in the 13th century, encountered Arabic numerals and recognized their power. His book, Liber Abaci, introduced the Hindu-Arabic number system to a Europe that was still clinging to Roman numerals, a system so cumbersome that it had all but stifled mathematical progress. Zero made arithmetic easier, and for that reason, merchants and bankers began to adopt it. But something else happened as well. With zero, mathematics began to break free from geometry altogether. For centuries, mathematical reasoning had been visual. Proofs were drawn, ratios demonstrated, relationships shown. But zero brought with it a new kind of thinking. Pure symbolic manipulation, in which numbers no longer needed a tangible counterpart. And so, by the time Europe entered the Renaissance, the transformation was complete. Mathematics was no longer something grounded in reality. It had become something abstract, rule-based, detached from the world it once described. This was the birth of modern mathematics. It was powerful, it was elegant, it was limitless. And it was also, in many ways, the beginning of mathematical alienation. It is easy to celebrate the introduction of zero as an unambiguous triumph. After all, without it, we would not have calculus. We would not have computers. We would not have modern physics or data science or the algorithms that shape our world. But what is less often considered is what was lost. Before zero, mathematics was intuitive. It was something an artisan could grasp, something an architect could feel in the stones he laid, something a musician could hear in the harmonies of his instrument. But after zero, mathematics became something for specialists. It became something to be learned in universities, something that required training in symbols and abstractions. The everyday person, who once used mathematics as a natural extension of thought, now saw it as an esoteric discipline, something arcane and difficult. Zero had made mathematics more powerful, but in doing so, it had also made it less accessible. This is the paradox we face today. Mathematics has never been more advanced, yet most people have never felt more disconnected from it. We have built a world where numbers govern everything, yet few understand how. And so, we must ask ourselves, was this the only path? Was there another way? Is it possible to retain the power of abstraction while reclaiming the relational, intuitive mathematics that once made the world comprehensible to all? To answer that, we must turn to the consequences of this transformation. We must examine how mathematics, once the tool of builders and navigators, became the domain of the intellectual elite, and how this divide continues to shape our world. For most of human history, mathematics was a skill practiced by artisans, architects, and navigators, people who used numbers as tools to shape the world. It was not an abstraction, but a physical reality, something as intuitive as balance, weight, and proportion. But as zero spread across the world, something changed. Mathematics, once accessible to all who built, measured, and observed, became the domain of an intellectual elite. It shifted from a practice grounded in tangible relationships to a system of symbols and rules, a structure detached from the very world it sought to describe. This was not an immediate transformation, nor was it entirely intentional. It was a slow, creeping shift, one that began in the medieval world and culminated in the modern age. And it is a shift that, to this day, continues to shape who understands mathematics and who does not. When zero arrived in Europe, it did not immediately change the way people thought about numbers. It was first embraced by merchants and accountants who saw its value in bookkeeping and trade. With zero, they could keep more precise records, track debts, and calculate interest in ways that were previously cumbersome. But while the merchants embraced zero, the builders, the masons, the engineers of the medieval world did not. The great cathedrals of Europe, the towering marvels of Gothic architecture, were not designed using algebra or decimal notation. They were not drawn from equations filled with zeros, nor were they calculated with place-value arithmetic. They were built the way their ancestors had built before them, with ratios, proportions, and geometric intuition. A master mason did not need to solve for X. He needed only to know that a structure twice as tall required a base twice as wide. Mathematics, for these builders, remained a physical craft passed down through generations. The master knew which ratios produced stability. The apprentice learned by measuring, by cutting, by seeing the relationships firsthand. To them, zero was not useful. It was in the universities, not in the workshops, not on the construction sites, not in the markets, that zero took hold. And it was here that mathematics began its long march toward abstraction. As Europe emerged from the Middle Ages, a new class of mathematicians began to appear. Scholars who were not builders or merchants, but theorists. They gathered in universities where they studied not proportions and tangible structures, but symbols, formulas, and abstract rules. They wrote about mathematics rather than practicing it with their hands. They debated concepts that had no immediate application: negative numbers, imaginary roots, infinities. Mathematics, once a tool for doing, became a discipline for thinking, and with that shift, the divide between practical mathematics and theoretical mathematics widened. The everyday person, the builder, the sailor, the merchant, continued to use the old ways. They measured by hand, they worked in ratios, they trusted their intuition, but the new mathematicians spoke a different language, a language of abstractions, of equations scribbled on parchment, of symbols that no longer had any connection to physical space. And as these theoretical methods became more advanced, they also became more exclusive. Mathematics was no longer something one could grasp intuitively. It became something one had to be taught. To learn mathematics now meant to study symbols, not shapes, to master the rules of abstraction, not the principles of proportion. And so, over time, mathematics ceased to be a universal language and became instead the domain of a learned few. For a time, these two worlds, the world of practical mathematics and the world of abstract mathematics, existed side by side. In the Renaissance, great artists like Leonardo da Vinci and Filippo Brunelleschi continued to use the ancient geometric methods. They rediscovered Greek and Roman texts, reintroducing proportional thinking into art and architecture. They understood perspective, symmetry, and ratios, not as numbers on a page, but as principles embedded in the natural world. But at the same time, abstract mathematics was advancing. Descartes introduced the Cartesian coordinate system, blending algebra with geometry, laying the foundation for a new way of seeing mathematics, one in which space itself could be represented numerically. Newton and Leibniz developed calculus, a system so powerful that it allowed for the precise mathematical description of motion, gravity, and change. Yet despite these advancements, most people did not use these new methods in daily life. The Renaissance painters still relied on visual intuition. The architects still worked in harmonic ratios. The sailors still used proportional navigation, not algebraic functions to chart their course. Mathematics was advancing, but it was also moving further and further away from the people who once used it instinctively. By the 19th century, the two worlds of mathematics had grown so far apart that they were nearly unrecognizable to one another. The builders, the craftsmen, the artisans, they still worked with proportions, rules of thumb, and intuitive measurements. They still used the mathematics of the past, but the mathematicians, the scientists, the engineers, they were now working with a new mathematics, one built on zero, algebra, calculus, and symbolic abstraction. This was the era of industrialization, and with it came an increasing need for mathematical specialists. Engineers now required formal training in differential equations. Scientists worked with complex variables and statistical models. Mathematics had become indispensable to progress, but it had also become inaccessible to all but a select few. And this is the world we live in today. A world where mathematics is more powerful than ever, yet feels distant and obscure. A world where most people see numbers as something imposed upon them, rather than something they instinctively understand. A world where mathematics, once the shared knowledge of builders and navigators, has become the guarded domain of specialists. This is the paradox of zero. It gave us immense power, yet it also divided us. Before zero, mathematics was universal. It was a language spoken by all, understood through the simple relationships of the world around us. After zero, mathematics became specialized. It became something one had to be taught, something with rules and symbols that no longer mapped directly onto the world. And as mathematics became more advanced, it also became more alien. Today, most people fear mathematics. They see it as a set of incomprehensible formulas, a system of rules with no clear connection to reality. They struggle with it in school. They avoid it in life. Yet this was not always the case. Once, mathematics was intuitive. Once, it was the foundation of creation, the tool of every craftsman, the guide of every traveler. And so we must ask, can it be so again? Must mathematics remain an elite language spoken only by the trained few? Or can we reclaim what was lost? Can we restore mathematics as a tool of intuition, of proportion, of natural understanding? To answer that, we must look forward. We must ask how to bridge the divide, how to merge the power of abstraction with the accessibility of relational thinking. We must seek a way back, not to reject zero, but to restore balance. For most of history, mathematics belonged to everyone. It was the language of builders, sailors, merchants, and astronomers, a practical, intuitive craft, passed from master to apprentice, shaping the world with its simple truths. But today, mathematics feels different. It is no longer something most people use instinctively. Instead, it is the domain of specialists, housed in universities and research institutions, guarded by the trained few who can navigate its complex symbols. How did we get here? The shift did not happen overnight. It was the result of a long historical process, a process in which mathematical knowledge, once shared, became increasingly concentrated in the hands of an intellectual elite. A process in which the relationship between numbers and the physical world faded, replaced by layers of abstraction, until mathematics became something that ordinary people no longer recognized as their own. It is a process that began long ago, but whose consequences shape the world we live in today. For centuries, mathematics had evolved along two parallel tracks, the practical and the theoretical. The artisans and engineers had continued to use the ancient proportional methods, while the scholars had developed algebra, calculus, and symbolic abstraction. But in the 19th century, these two worlds collided. The Industrial Revolution demanded more than intuition. As machines grew more complex, as cities expanded, as bridges and railroads stretched across continents, the old ways of proportional reasoning were no longer enough. Industry required precision. Factories required efficiency. The world was moving faster than ever, and mathematics had to keep up. And so, for the first time, formal mathematical education became a necessity. No longer could an engineer rely purely on experience. He needed to understand differential equations, load-bearing calculations, and probability models. No longer could a navigator rely solely on the stars. He needed to understand spherical trigonometry. The result was a shift unlike any before it. Mathematics, which had once been a skill learned through practice, now required formal training. Universities became the gatekeepers of mathematical knowledge. Apprenticeship gave way to degrees and certifications. Mathematics was no longer for everyone. It was now the tool of those who had the time, the resources, and the education to master it. And as this process accelerated, something strange began to happen. For the first time, mathematics became a field unto itself, not just a tool for engineers and scientists, but a discipline practiced by mathematicians for mathematics' sake. It was no longer just about solving problems in the real world. It was about exploring the abstract, the theoretical, the infinite. And with this shift, the divide between the practical and the abstract became wider than ever before. As the industrial age progressed, a new kind of thinker emerged, the pure mathematician. These were men and women who did not build bridges or design machines. They did not navigate ships or construct buildings. They worked with numbers as concepts, exploring patterns, proving theorems, constructing systems of logic that had no immediate application to the physical world. For some, this was the highest achievement of mathematics, to transcend the limits of reality, to uncover truths that existed beyond the material. But for others, it marked the moment when mathematics truly became detached from its origins. For centuries, even the most theoretical of mathematicians had still worked with numbers that described the world. The Greeks had their geometric forms, the Babylonians had their astronomical cycles, the Renaissance thinkers had their proportions and harmonies. But by the late 19th and early 20th centuries, mathematics was moving into new territory where numbers no longer had to represent anything at all. Mathematicians began to explore non-Euclidean geometries that described spaces that did not exist. They formalized set theory, constructing infinite collections of numbers beyond anything that could be counted. They developed abstract algebra, where symbols interacted according to purely logical rules, untethered from physical interpretation. Mathematics had become a game of the mind, an art form of its own. And while this led to extraordinary breakthroughs in science and technology, it also deepened the divide between those who understood this new mathematics and those who did not. For the first time in history, the ordinary person could not recognize mathematics as something useful, something familiar, something that connected to their daily lives. Mathematics had become the language of the elite. In the 20th century, mathematics underwent yet another transformation, one that would make it more powerful than ever, yet even more inaccessible. The rise of computers transformed mathematics from a discipline of thought into a force that governed the world. With computers came data, algorithms, and automation. Zero, once a mere placeholder, became the foundation of digital logic. The binary system, just ones and zeros, became the language that powered industry, finance, and communication. And yet, as mathematics became more embedded in daily life, fewer people understood it. The numbers that once measured land and grain now existed in hidden algorithms, running in the background of society. Equations no longer described physical relationships. They determined stock markets, controlled artificial intelligence, shaped economies, and influenced global politics. And who controlled these numbers? Not the artisans, not the builders, not the everyday citizen, but a small group, the technologists, the scientists, the data analysts, the mathematicians. Mathematics was no longer just knowledge. It was power. And with that power came a question, one that echoes through history. If mathematics now governs the world but only a select few can understand it, who truly controls the future? We live in a world shaped by mathematical abstraction. Every transaction, every piece of technology, every decision in modern life is, at some level, determined by numbers and algorithms. And yet most people are cut off from this reality. They use technology without understanding how it works. They accept mathematical models without questioning their assumptions. They trust numbers without knowing where they come from. This is the final consequence of the rise of the intellectual elite in mathematics. It has left the majority of humanity mathematically powerless. Once, mathematics was something a person could see, touch, and intuitively grasp. Now it is hidden behind layers of abstraction, accessible only to those with the training to understand it. And this brings us to the final question of our journey. Can this divide be bridged? Can we restore the accessibility of mathematics without losing the power of abstraction? Or are we destined to live in a world where numbers rule over us, rather than a world where we rule over numbers? To answer that, we must look toward the future. We must ask how mathematics can be reclaimed, not just by specialists, but by everyone. Mathematics is everywhere. It powers our cities, our industries, our digital lives. It is the foundation of science, the engine of technology, the invisible architect of modern society. Yet for all its power, mathematics today feels strangely stuck. Gone are the days of foundational breakthroughs that shook the world. The age of Newton and Leibniz, of Galileo and Euclid, feels like a distant memory. Modern mathematics, despite its vast computational reach, seems trapped in abstraction, endlessly spiraling into deeper complexity, but offering diminishing returns in its ability to describe the world. And so we find ourselves at a crossroads. Mathematics has never been more powerful, but it has also never been more distant. Distant from the people who rely on it, distant from the physical realities it once sought to explain, distant from the curiosity and wonder that once defined it. How did we arrive here? And more importantly, how do we find a way forward? The answer lies in a pattern we have seen unfold time and again throughout history. Each time mathematics has grown too abstract, too specialized, too disconnected, it has left behind the very people it was meant to serve. And each time this has happened, the consequences have been the same: stagnation. We see it today, all around us. In schools, mathematics has become a source of frustration rather than inspiration. For most students, it is not an exciting language of discovery. It is a barrier, an endless sequence of drills and rules, stripped of meaning and connection. By the time they leave school, most people view mathematics as a chore at best and a mystery at worst. In science, the symptoms are just as clear. We have amassed mountains of data but struggle to turn that data into new ideas. In physics, we chase abstract theories of everything, mathematical constructs so distant from observation that they often feel like speculation, not science. Even in biology and medicine, where computational power has transformed research, we often find ourselves drowning in complexity without truly understanding the systems we study. And in society as a whole, mathematics has become a tool not of empowerment, but of control. Algorithms shape our lives without explanation. Financial models determine the global economy, understood by only a handful of experts. The mathematics that once guided sailors across the seas now governs the digital systems that decide what news we see, what products we buy, even how we think. Mathematics has become a black box, powerful but opaque, vital but incomprehensible. And for most people, it feels alien, a force imposed upon them rather than a tool they can wield. If we are to move forward, if we are to break free from this stagnation, we must return to the roots of mathematics, to the relational, proportional understanding that once made it accessible to all. This does not mean abandoning abstraction or rejecting zero. Far from it. Abstraction has given us extraordinary tools, and zero remains one of the most powerful ideas ever conceived. But abstraction alone is not enough. It must be balanced with intuition. It must be connected to the world it seeks to describe. Mathematics must once again become a way of seeing relationships, not just manipulating symbols. Imagine an education system where children learn not by memorizing formulas, but by experiencing mathematics in the world around them, where fractions are understood through dividing loaves of bread, not pages of a textbook, where geometry is taught not as abstract proofs, but as the study of the shapes and patterns that surround us. Imagine a mathematics that bridges the gap between theory and intuition, where algebra is not a set of lifeless equations, but a way to describe patterns in nature, where calculus is taught not as an endless stream of derivatives and integrals, but as the story of motion, of rivers flowing, of planets spinning in the heavens. This is not about making mathematics easier, it is about making it visible. It is about restoring the connection between numbers and the world they were meant to describe. For too long we have treated abstraction as the pinnacle of mathematical thought. But history tells us that this is only one side of the story. The Greeks, with their focus on geometry, saw mathematics as a way of constructing the world. The Renaissance thinkers used proportions to capture the harmony of nature and art. Even the architects of the Industrial Revolution relied as much on their intuition as they did on their equations. Each of these eras found balance between the abstract and the relational. And it is that balance we must seek once again. We must embrace the best of both worlds. The precision of symbolic logic and the accessibility of proportional thinking. The power of abstraction and the clarity of intuition. Because when we do, we will not only reclaim mathematics as a universal language, we will unlock new ways of thinking, new ways of seeing, and new ways of understanding the world. For centuries we have taken it as a given that zero was one of the greatest advancements in mathematical thought. We have built entire disciplines upon it, expanded it into decimal notation, embedded it in our equations, and woven it into the very foundations of our modern world. But what if we were wrong? What if instead of an advancement, zero was a corruption of mathematical precision? What if instead of bringing us closer to truth, it led us further away? Through our journey, we have seen how the mathematics of the ancients, grounded in ratios, in geometric relationships, in proportional reasoning, produced extraordinary achievements. The pyramids of Egypt, the celestial predictions of the Babylonians, the architectural harmonies of the Greeks and Renaissance builders, none of these required zero. They did not require place value notation or decimal approximations. Yet, with the introduction of zero, mathematics underwent a profound transformation. It was no longer about describing relationships that naturally existed. It became about constructing a numerical system that required constant correction. It gave us ease of calculation, but at the cost of distorting the very reality it was meant to model. Because zero in its very nature does not represent anything real. It is an absence, a void, a concept that has no direct counterpart in the physical world. And by embedding that void into our numerical system, we introduced an error that has only compounded over time. We have spent centuries refining the mathematics built upon zero, correcting it, compensating for its distortions, layering new abstractions atop its flaws. But all of this assumes the foundation itself is sound. And what we have now revealed is that it is not. We see the consequences of this unstable abstraction everywhere. Modern physics, once driven by direct observation and proportional reasoning, now finds itself trapped in abstract models, filled with infinities and singularities, mathematical artifacts that arise not from nature itself, but from the structure of the notation we use to describe it. Economics, governed by decimal approximations and numerical models, repeatedly fails to predict crises, not because markets are unknowable, but because our tools distort the reality they attempt to measure. Even in simple arithmetic, we find ourselves constantly managing rounding errors, infinitesimal approximations, and the contradictions of irrational numbers, problems that would not exist if our system were based on relationships rather than absolute positions in an invented space. We have mistaken computational convenience for mathematical truth. And in doing so, we have lost sight of the methods that once gave us precision, clarity, and understanding. It is time to correct this mistake. The answer is not to simply supplement decimal mathematics with proportional reasoning. The answer is to discard zero entirely and return to the mathematical systems that we know produced real, tangible, and lasting achievements. We must reclaim the mathematics of ratios, of harmonic proportions, of geometric construction, a mathematics grounded in the relationships that actually exist in the world, rather than the invented placeholders of an abstract numerical system. This is not a step backward. This is a return to precision. It is a rejection of the artificial distortions that zero introduces. It is an acknowledgement that the ancients did not simply fail to invent zero, but that they recognized its flaws and chose not to use it. And it is a call to rebuild mathematics from its foundations, to restore the balance that was lost, and to once again see numbers not as detached symbols, but as reflections of the real, measurable, and proportional world. The mathematics we need is not the mathematics we have been given, but it is the mathematics we once had, and it is time to reclaim it. The choice before us is clear. We can continue on our current path, refining and complicating a flawed system, forever trying to patch the cracks in a foundation that was never stable to begin with. Or we can take a different path. We can recognize that the distortion began with zero, that every abstraction built upon it has only magnified its instability, that mathematics does not have to be this way. And we can choose to return to what works, to the mathematics of the ancients, to the mathematics of relationships, of proportions, of precision, to a world where mathematics is once again a tool for understanding, not a system we must constantly correct. The numbers will still be there, the relationships will remain, but the illusion that zero is necessary, that zero is fundamental, will be gone. And in its place we will find something far greater, a mathematics that is finally and truly real. That is the path forward. The only question is whether we have the courage to take it. It is time to reclaim what was lost. It is time to abandon the unstable abstraction that has distorted our understanding for centuries. It is time to return to a mathematics that is, once again, precise, intuitive, and real. This is not the end of mathematics. It is the beginning of something new, or rather something very, very old, and it is waiting for us to rediscover it.